Thank you very much. Okay, so this is billed as a sort of beginner level talk, but what I'm going to try to do is sort of delve into some of the details fairly quickly. So we haven't got long as ever, so I'm going to kind of dive straight in. So this was the abstract. I wanted to talk about lock weights, deadlocks, serializable errors and such like, and what you do about them. So this is really aimed at application developers and those of us that have to deal with them when they get it wrong. So what is contention? Well, Postgres is designed to support multiple sessions with concurrent access to the database. And so if we access the database for read-write, then we get various effects coming out. Generally, if you do read-read access between two sessions, then there's not really any contention, okay? Not a true statement, but true enough for this talk, okay? So there's various areas that I could talk about that I'm not going to. If there's reads and writes going on, then Postgres already addresses this via the MVCC system, which means that the reads are not blocked by the writes and the writes don't block the reads. The problems come when you have two sessions both performing or trying to perform writes against the same data elements at the same time. And what we're going to do is have a look at the effects of that in various parts of the system. So the contention comes when you've got two things trying to do the same thing at the same time. And an example of that is fairly straightforward. If you've got two sessions both performing an update transaction at exactly the same time on exactly the same data, then you're going to get a lock wait. Obviously, if they're even 10 milliseconds apart, you don't get a lock wait, okay? So they have to happen exactly concurrently in order for there to be contention. Now, obviously, there are also various physical effects within the database manager, and I'm not really going to talk about any of that stuff in this talk, okay? So this is all about application contention and lock weights caused by data locks. So how do I know that waits are happening right now? Well, there's a virtual table called PGStat activity, and it's got a couple of columns in it, the wait event type and the wait event, and that describes what an application is waiting on. Now, those are set momentarily, right? So if you get a lock wait of, say, 7 milliseconds, then you're going to have to be real quick to spot that in PGStat activity. But obviously what will happen is over the course of thousands of transactions and hours of time, you will see some kind of a pattern in the wait events that you see emerging. So you can't really see individual events, but that's okay. It's kind of like you're not trying to see individual photons, you're trying to get a whole pattern of the millions of photons that you see. There's also another table called PG locks, where there's a wait start column, which is strangely named, but it's a timestamp column of when the wait started, and also the granted column is a Boolean that will be set to false when the lock is waiting and was not immediately granted. One of the strange things is that the wait event is not set correctly for tuple locks. Actually, what this shows is that it waits on a transaction ID. That's rather difficult to explain, but I'll have a go at it. When we try to lock a tuple, we read the tuple and we see that there's already somebody else locking it, and that's got a transaction ID on it. So when you wait for the tuple, you actually wait for the current holder of the lock. Okay, and so it shows as a transaction lock rather than as a row lock, but actually that's what it is a row lock. How do I know lock waits happened in the past? Well, there isn't a way to accumulate statistics on the system, so we don't actually keep track of lock waits that have occurred. What we do though is there's a parameter called log waits, which I introduced about a decade ago, and that will log anything that's longer than the deadlock timeout. And the deadlock timeout is set by default to 1 second. So if you're getting contention that's consistent but always less than 1 second, then it won't ever show anything in the log from this this mechanism. So this really shows when the locks themselves are really quite long. So something that we might want to consider doing in the future was adding some accumulated statistics for particular types of lock wait. Because there were quite a lot of developers here, I've actually kind of gone through my notes here and spiced up a few, we could do that in the future. So if you're like wondering why I'm telling you that Postgres is half finished, it was kind of like these are little sort of seeds to other developers like going, you could go and work on that, hint, hint. So how long do the locks wait? Well, they start from when you take the lock and they end at commit. So if you're taking multiple locks in a transaction, then the first lock you take will last the longest, then the second lock, and then the third lock, etc. So multiple actions in a transaction make the waits last longer because obviously the whole transaction is lasting longer as a result. So the bigger, the fatter the transaction, the more, the longer the duration of the lock waits that you will see. And obviously, if you batch together transactions, doing lots of actions inside one transaction, then the lock waits will grow substantially as a result. Now, that can be more efficient in terms of the resource utilization, but it could be counterproductive because of the lock waits that you get. So you need to optimize the batches to a reasonable size. High availability affects this as well because two-phase commit, or otherwise known as prepared transactions, will hold locks across distributed transactions, and that is especially difficult if one of the participant resource managers crashes, because then the locks don't go away. That's the whole point of prepared transactions. So lock contention will stay while that system recovers from crashes. So if your database system is going to take 2 or 3 minutes to come back up, then you should expect locks to wait that long in the course of a crash. Synchronous replication also holds locks while you're waiting for acknowledgement from the remote system, and that will give you significantly longer latency for your transactions, and therefore for the lock waits that would be produced by that. And what you'll find is that typically the system can manage each statement in typically less than 1 millisecond, but you might easily see 10 to 50 milliseconds of synchronous waiting time. So the actual duration of the lock wait, and therefore the contention, could be 100 times larger as a result. So this can be a problem if HA is added as an afterthought to applications. So how does all this affect applications then? Well, in a couple of different ways. Obviously, the app dev always says, it worked on my laptop, I can't understand why it doesn't work in production. And then we'll laugh uncontrollably at how ridiculous that statement is. But everybody says it at least once in their life, right? So the effects that this has is that if you've got multiple sessions all accessing the same data, then the amount of contention you get goes up as the square of the number of concurrent sessions. Okay, so if you go from 2 sessions to 64 sessions, then you're going to really significantly increase the amount of contention on the system. And at the same time, if you increase the latency of transactions, that increases the contention also as the square of the duration of the lock window. And so what you find in a lot of cases with synchronous replication is, because synchronous replication is slow, you add more sessions in order to make up the throughput. And then you've got both very long transactions and more sessions involved. And so actually you can get significant contention arriving just simply because you enabled synchronous replication. What's worse about all of this is contention can show itself only in periods of high traffic, at certain times of day, or with certain access patterns. And that can be the most confusing thing, because it looks like Postgres just slows down every so often. 3 o'clock in the afternoon, Postgres slows down, and you've got no idea why. So at this point, most people run away and say, oh, I'm giving up, Postgres is crap. What are you telling me? All this, like, it's latency and it's contention. My God, I'm going to use a proper database like Mongo. And then, obviously, then you wake up and you realize that a database can be scalable, but your application still needs to be written to be scalable on top of that scalable database, okay? And one of the reasons that Postgres hasn't scaled is that a lot of the access types that you get in a higher function relational database include things like range scans that just simply don't work. They're not even available on some of those systems like Mongo, where in order to get the scalability, they simply ban you from asking certain types of query, okay? And because in Postgres we allow you to ask all manner of different types of query, and some of those types of query don't scale. So when we eventually do have fully scalable Postgres in core, you will see that there are restrictions on the type of activity that you're allowed to perform in order for it to be scalable, okay? So there's no magic button that you can push and just say, I'm going to have my scalable application now. You've got to have a scalable database, and you've got to have an application that's designed properly to use that application schema. And it may not be possible, because you may have requirements that are firmly part of the business requirements for the system that actually prevent that scalability. So obviously, things that you need to watch. And, you know, this is basically, that's why DevOps exists, because writing stuff in dev and then just handing it over the fence to somebody never worked. So let's have a look at loads of things that really don't work. So, conversational transactions. Imagine an application where, as you start to fill out a form, it starts a transaction, and as you fill out page after page after page of data in this application, it holds locks for the whole duration of that. So it's holding locks across human interaction. And in that case, it's so awful that no one even thinks of doing this, because it's so awful. But just for completeness to say, this is very slow and it produces huge contention, and that's really why no one does it. But you can still have conversational transactions with the app tier, where an application is issuing SQL from the application server, and there's pauses while we go back to the app tier and ask for the next statement, and it returns things, does a bit of logic, and that kind of sucks as well, but not quite as badly. And one of the ways of solving that is to minimize the network distance between the app tier and the database. But this is where server-side procedures come in, and some people have seen things like PLSQL as just a straight attempt by Oracle to lock you in with an evil plan to put applications onto the server. But the reality is that server-side procedures are extremely clever because they minimize to absolutely zero the logic between SQL statements. And so server-side procedures or functions are a great way to reduce contention and therefore increase performance, okay? So the real role of server-side logic is related to performance, not related to lock-in. Obviously, you might say, well, that's just a beneficial side effect, right? But no, I mean, seriously, I've seen people that absolutely mandate that they will not use functions and procedures for various reasons, and then their applications suffer from these problems and they can't understand why. So if we can't measure the effects of concurrency easily, then we need to take some practical steps. And this is where you need to do performance testing, full performance testing on your applications at scale with realistic data to find out what is going to happen. Now, I say realistic data because one of the things that quite often happens in performance testing is you generate purely random data that is that doesn't experience any hotspots at all because it's all purely random, and then you go into production with real data and you've suddenly got hotspots and you can't explain it because you took it up to 50,000 TPS and it worked, and you can't really understand what's going on. But just to mention that there isn't really a formal way to assess the impact of contention on your applications. You need to look at the overall latency. So if you are using PGBench, as I'm suggesting, then look at the latency statistics that are coming back from that, and also looking at the PG statement latency with regard to that transaction. So when it's running with concurrent sessions, then you will see the SQL statements will grow in execution time, whereas when they're running individually, they'll execute a lot faster. So you don't see the contention directly, you see it implicitly within the total latency of each statement. So let's talk about deadlocks. If you have transactions that do multiple actions in, then you can get deadlocks. You can't really get deadlocks if your transactions only do one thing, because the key point of a deadlock is one transaction needs to hold two locks, and then the other transaction needs to be attempting to access that other data. And when the data is accessed in a slightly different ordering between those two transactions, then the second transaction goes into a wait state, and there's no way out of that, okay? The only thing that happens is, by default, you will hit the deadlock timeout after 1 second, and it will go through a deadlock cycle, and then one of the transactions will kill itself as a way of resolving that deadlock. So, a few things to say about that. The deadlock detector locks the whole lock table in shared memory, which means that it will need to access 16 different lightweight locks in a specific order, and those are the locks that are held when a database does lots of I/O. So the deadlock detection itself can take a significant amount of time just simply to the lock table. And then when it's done that, it will probably resolve the deadlock fairly quickly. Now, the worst thing that happens is if you get a deadlock situation where the deadlock detector is called, but there isn't actually a deadlock, because then it takes ages to lock the lock table, and then it does nothing. Worse than that, every execution of the deadlock detector only looks at the caller's locks. So if there are multiple people with deadlocks in the system, then they won't all get resolved on that one execution. And so you end up with a deadlock storm occurring. So in some situations, you may need to set the deadlock timeout a lot higher. And what you'll see is if you try to execute a DDL statement, then a lot of transactions will pile up behind that DDL statement, and they'll all hit the deadlock detector, and there'll be a deadlock storm behind that. So that's one source of quite a lot of contention. And I had a long list of suggestions for further improvement in the deadlock detector code. So how do I know deadlocks happened? Well, you see log messages because a deadlock will fail with an error, and it does tell you lots of useful information like process 6855 waits for access exclusive lock on relation 16394. Nice human readable, easy to understand logic that really helps you to understand what's going on. Luckily, there's a column on PGStat database that counts the number of deadlocks that have been experienced, but it doesn't show what table the deadlocks were accessing at the time of the deadlock. So again, it would be really nice to have contention information at the table level so that we would be able to see what's going on a bit better. In order to avoid deadlocks, you just need to lock the objects in a consistent order, both at table level and at row level. So you might need to add order bys to some of the queries in order to get that locking to be consistent. There isn't any way to tell that a particular transaction is a deadlock risk. So again, that would be a nice feature. One of the things you might want to do is sort batch inputs as a way of potentially avoiding deadlocks as well. And it's also possible to get into thread deadlocks where you run multiple sessions into the database from a single program, and then you basically deadlock yourself across those sessions. So that's easily done as well. So let's have a look at some application design anti-patterns. Basically, the types of things that cause hotspots in the code. Well, bank transfers are one. If everybody transfers money to the hotel, you'll see that hundreds of people are transferring money from their account to the hotel's account, and the hotel's account is obviously going to be a hotspot in that situation because it's going to have hundreds more transactions per time unit than individual payers. Social media, for example, obviously if there's some really seriously famous people with hundreds of millions of followers, if they do anything, then that is going to cause a huge hotspot on those individual records. Another situation is where you're keeping track of a summary total. So every time someone does a transaction, you add up a total of the effects of the individual transactions. Again, that really, really doesn't work. As an example of that, I worked with a company that had set up a chat room application, and because they thought it was a great requirement, on each chat room they kept track of the current number of people in the chat room, which worked fine when there were a small number of people in the chat room, and then somebody had the bright idea to invite somebody really famous to appear in one of their chat rooms, and that really famous person turned up, and then all of a sudden they had hundreds of people all trying to connect to the chat room at the same time, which caused huge contention, which meant the app apparently froze. It wasn't frozen, it was just heavily contended. And then while people were waiting to enter the chat room, they then decided that the thing was broken and that they would leave the chat room again because nothing was happening in the chat room. So you had a load of people trying to get into the chat room and also another load of people trying to get out of the chat room because nothing was happening in the chat room. And the whole thing just ground to a complete halt, and no one could understand why. And obviously, when you see that this was simply down to the clever guy that said, let's keep track of the number of people in each chat room. And as soon as they commented out that section of the code, it all worked, okay? Because that reduced the contention and everything worked. So real-time update of summary values is a really bad idea, and that's why real-time update of materialized views isn't a function in Postgres, because if it did exist, it would be crap, okay? So another application design pattern is where we do a select statement with a write lock for update, and then later come back and do an update. So obviously when we do that, the lock window on that particular row lasts significantly longer, and that's why it's a good idea to do that as a single update statement with a returning clause on it, because the lock window is held for a shorter amount of time, and therefore it is both more efficient and lower contention. Another aspect of tuning is to replace logic like this, where you say insert, and if it fails with a unique violation, do an update, otherwise known as the classic upsert case. And Postgres specifically provides a feature to do this efficiently and accurately, and that's the insert on conflict statement. The only downside to this is that it always inserts first, which may not be ideal for high update percentage chances. So you might, in some cases, want to go back to the other older coding. So that's everything I was going to say about lock weights and lock contention. Now I'm going to talk about serializable transactions. So in ACID, we have atomicity, consistency, isolation, and durability. And the transaction isolation level is something that you can set with your application programs, and it controls what types of visibility anomaly that you can get from concurrent sessions. Most people lost me somewhere after the first 10 words in that statement, and I've had a lot of people that thought they know how transaction isolation works and unfortunately were wrong. So default transaction isolation in Postgres is read committed. This is also the default in Oracle, which is why a lot of people don't know about serializable or high levels of transaction isolation. So read committed allows you to see the latest version of the rows in the database, but it does allow certain anomalies to occur. So historically, the only way to handle that was to try and lock everything yourself to avoid the error. But Postgres was actually the first database to introduce full serializable mode in 2009, based on a PhD thesis that showed a feasible algorithm that we could use for detecting it. Now, some people have said that actually serializable mode's a really good thing, because you just flip the switch, put it into serializable mode, and then it does a really nice thing, which is it throws errors if there's any contention that affects it. Now, the nice thing there is it's accurate. Yeah, if you have to go through your application logic, sprinkling little lock statements in the appropriate places, you basically got no hope of doing that correctly, because it's quite complex, and most people either put too many in or too few, and you either get poor performance or wrong answers out of the system. So it's pretty cool, but the impact of serializability is that it will throw more errors, and what tends to happen is that the people that tell you that serializable is a really good idea just don't mention the extra errors that you get from contention. So serializable transactions literally turn application contention into errors, okay? And that is not particularly useful, because the errors themselves are logged, but the count of the serializable errors aren't logged. There's no sort of summary statistics like there were for deadlocks. So we're missing a few features with regard to kind of keeping track of some of this stuff. So you get a transaction serialization error, and the good news is it's a retryable error. So all you need to do is re-execute the transaction and everything is fine. But obviously you need to re-execute the transaction, and if it got an error because you had transaction contention, you could get another error when you resubmit it, and another error, and another error. Okay, and depending on how much contention you get, you basically might be in a position where the transaction rate you think that you would like, you can't ever achieve, because all these concurrent sessions are all knocking into each other and generating huge contention on the system. So it's lovely that it's a retryable error, but it doesn't mean it's feasible to retry. Okay, so certain workloads will experience very serious numbers of errors from serializable transactions. And what's worse is that it isn't always correct to immediately re-execute the transaction, because the transaction might have had values in it that were calculated by reading data on the database. So if you read the value and said, oh, that value's 7, so I'll add 1 to it, so now I'll set that to 8. Well, if in the meantime something happened on the database, it's not the value 8 that you need to add to the database anymore. It's +1 from whatever it was, right? So now you're into the difficulty of saying, is it correct to actually re-execute the SQL in the way that we envisaged? And that's difficult to assess. Does the SQL use reflexive logic, for example, column equals column +1, or does it just say column equals value, right? And if it's the second one, then you've got potentially significant problems. Worse than that, some of the functional logic might have threshold values in it where it does a certain thing below a particular value and it does a different behavior above a separate value. So what's going to happen there? The transactions actually execute differently. So what we think is that automatic re-execution of SQL is not automatically correct. And that's why there isn't a feature and won't be a feature in Postgres that automatically re-executes things after a serializable error. Now, this is where I wanted to have a look at a system that advocates purely serializable transactions in all cases, okay? And what we have is some comments there from somebody that tried to get their application to work using CockroachDB, and we had to add retry error logic to the application to get it to work. And it says, we experience much more transaction contention with CockroachDB and therefore aborted transactions and also slower performance with some of our database access patterns. And we encountered some unusual behaviors where we had long-running queries taking over 2 hours sometimes, stalled transactions that never completed, okay? So one of the things that we will be doing in Postgres is improving support for serializable transaction modes. But this is not a magic bullet, okay? And when people start telling you that distributed systems must work with ACID because it's the only way, it's not really true, because application contention can completely destroy the performance and usability of some of those systems, okay? So I wanted to present that to you to really sort of make you think about some of the things that people are saying about Postgres and the way that Postgres approaches things. And I might mention at this point that Postgres-BDR, which is, as you probably heard, a distributed database built on Postgres, actually offers a number of different approaches to handling application contention in a distributed manner. Specifically, BDR has been criticized because asynchronous transactions handle contention via conflict detection and resolution. And people have said, well, that's, that kind of doesn't work because of this, and wouldn't it just be beautiful if it all just happened wonderfully in the background? Well, the reality is that this is a really good way of doing it because it's fast, and if you don't get contention, then it's basically an optimistic approach to distributed systems. But BDR has also got things called conflict-free replicated data types that are specially designed, thank you to Thomas for writing them, by the way, specially designed to handle the high contention cases. So instead of rejecting application contention with errors, it actually handles that correctly and gives correct answers even under higher levels of contention. Anyway, I'm just going to skip to the fun bit, which is a performance test that we did with CockroachDB versus Postgres, Postgres-BDR in this sense with synchronous replication. And on a sort of stable performance, we managed to get 1,600 transactions within 200 millisecond limit on CockroachDB, and on the same hardware, but just using the different database software, we got 16,000 transactions with a transaction latency significantly lower than that, and almost no skipped or late transactions. So the conclusion from all of this was that CockroachDB was about 10 times slower than Postgres, okay? And that's when it's working, okay? And that's not when you take into account what I'd said about the serializable transactions. So you may well say at this point that you're just rubbing in, you're just crowing about better performance and that kind of thing. But what I've been hearing is that people are being told that distributed consistency is this nirvana that gives you everything you absolutely need, and the way that Postgres doesn't support these things yet is a massive problem that should mean that we don't pick approaches like Postgres. So what I'm trying to point out here is the best case is Postgres is significantly faster, but this is running with synchronous replication, so you're still getting the same levels of data protection from it, and yet it doesn't suffer the effects of application contention that you could get with some designs of application. So what I've tried to do in this talk is to take you through a lot of issues that can occur with applications. And what I've spoken to a number of people over the last few years where the application was actually the reason why they got contention, poor performance, and slow latency. And actually, what I wanted to try to do is to explain to people that the SQL that you issue, when you issue it, how you issue it, and what data that SQL affects has a real effect on the database system. Postgres is pretty cool. It's got some physical issues that we are in the process of improving over release after release, right? But one of the largest effects that you will see is really to do with application design itself, and that there isn't a magic bullet out there where the database just does everything for you and you can completely relax, okay? That's not true, okay? So what you need to say to people is Postgres is pretty cool and more work is always needed, and I can see many years of work for us as a project to continuously improve where we are. But what I don't see is that magic bullet. And what I am saying to people is that app devs must take responsibility for the contention in their applications and the performance that they will get in the real world, okay? So if you can take that message back to people, it's not to say it's not our fault, okay? You know, if you're using Postgres, then we care about the performance that you get out of using Postgres. But some things aren't possible for us to do anything about, given the API. Basically, Postgres is sitting there receiving SQL calls, and if you make SQL calls that are quite widely spaced, then you're going to get longer transaction latency and longer lock waits, okay? And that's not something that we can directly do anything about. So please take that message of responsibility back out there into the market and let people know that Postgres is a scalable database, but it does require scalable application development and scalable schemas to be designed in order to work smoothly and effectively. Okay. So thank you for listening without too much contention to the points that I've made. A final point I might mention is that the 6th edition of the Administration Cookbook is going to be due out in the next few weeks, maybe a month or so, okay? So definitely on sale early in 2022. It does say 3rd edition on there, but that's because the graphic artist got that bit wrong on this image, okay? But it's actually the 6th edition, and it's fully updated for Postgres 14 coming out soon. So, could I have questions, please? I'm happy to flick back to any of the slides I had and answer any specific questions that you have on the topics I've raised.
So if you have any questions, please raise your hand so that I could get you the mic. Yeah.
Regarding an investigation of timeouts and that sort of thing, are you aware of any extensions that exist to collect that data in a similar way to PGStat statements might collect query statistics?
So I think there are some log analysis applications like PGBadger that sort of trawl through the logs and collect up some of the log weight statements. But what I'm saying is that they only collect log statements that have been made. So if the contention was less than 1 second by default, there won't be an entry in the log, and it won't apparently show you anything. Okay, so I would sort of regard it at the moment as a sort of missing feature that we need to add to make that easier to get that information out in a usable way. So. Okay. Hi.
Just a quick question down memory lane. Didn't DB2 do a default serializable?
Well, I mean, there is a parameter that allows you to set the default transaction isolation in Postgres, so you can set that.
No, I mean back in DB2 times. Didn't they normally default to serializable?
I didn't think so. They had like cursor stability as one of the default modes, which is actually a slightly reduced form of isolation from read committed. So where it actually held the locks only while the cursor was traveling over the rows in a cursor. So I certainly don't remember what you mentioned. Having had the pleasure of working with DB2 at one point, so. Okay, it wasn't that much fun. Hi. Over there.
So a quick question about, simulating production contention or concurrency in a development environment. Are there any tools that take the approach of maybe trying to like throttle transaction speeds or like speeds of queries in order to simulate that, where we're not necessarily looking at TPS, but trying to like catch this in a development environment with maybe more limited resources?
Yeah, I mean, there have been some tools that attempted to capture the full execution of the database, including the sort of exact start of each statement. But the realistic truth of it is that's relatively hard to do. And obviously, if the system is under heavy load, the logging required to do that would be extreme, and it would have quite an effect on the performance itself. So probably one of the first things you do is turn that off. So it would be usable in pre-production, but not necessarily in production, because you wouldn't want to sort of turn on a very heavy logging thing just at the point where you experience performance problems. So the best thing that you can really do is to sample the output from the PGStat activity to understand exactly what's happening where within the system. So obviously, a lot of the diagnostic stuff, definitely around locking and things like that, as things that we've put into the system over a long period of time. So if you've got any specific problems that you would like help with, then I'm sure that we'd be happy to help with that. But obviously, I am looking at the features that we would need to put into the system to improve it in the future. So, if you've, out of some of the things I've said, if you wanted to kind of contact me and say, this one's more important than that one, I'd welcome that feedback. So, any other questions, please? Last chance. Okay, brilliant. Well, thank you for listening to everything I've said. I saw lots of nodding heads while I was speaking, and I can only tell you that's absolutely wonderful after 2 years of being away and just speaking at the Zoom camera, hoping that what you're saying makes sense to people. It is really nice to kind of get that feedback as we're here. So thank you very much for coming to the talk. If you want to find anything else out, buy the book, go to the EDB website, or write me a note or whatever, and we'll see if we can sort you out, okay? So have a good rest of the conference, and see you again next time. Thank you very much.